Here's a question that it asks us to use both the differential rate law and the integrated rate law and calculate half-life and do a few other things involving rate law. So this is a very comprehensive problem. First of all, if we read this carefully, they give us a really important fact. A slope of the natural log of concentration versus time gives us a straight line. Based on that fact alone, we know that we have a first order reaction. And that'll dictate all of the other answers that we work out. So if we just know that, and we know something about how which slope results in a straight line, and we know that there can only be one plot that gives a straight line for each of the different reaction types. And we know that it's a first order reaction, and up above they say, hey, the only reactant is the substance A. Then, okay, the differential rate law, for which the sum of the exponents is 1, is your first answer choice. The integrated rate law for all first order reactions takes this format. So we know that we have natural log of A equals negative KT plus the natural log of the initial concentration of A. And then one other quick one that we can do is they say, okay, your straight line has a slope of negative 2.97 10 to the negative second. Well, if you look closely, you can either know from your graphing results that the slope of the first straight line plot of a first order reaction takes the value of negative k. Or you can look at the rate law and note that it's written in the format y equals mx plus b. Well, what's the value of m? Negative k. The slope is negative rate constant k. So that means if we take the inverse, instead of a negative 2.97, make it a positive 2.97 times 10 to the negative second inverse minutes, you have your value of k. So without even doing any calculation, we've got the first three answers. Now to get the rest, we'll have to do a little work. Half-life. For a first order reaction, half-life can be found by taking the natural log of 2 over the rate constant k. This is the only reaction order type for which the half-life is constant. That's why oftentimes chemists or people who write chemistry problems love to ask you half-life questions about first order reactions. The natural log of 2 written out as a decimal is 0.693. And now that we know the value of k, let's just plug that in. 2.97 times 10 to the negative second. And this will come out in units of minutes because the value of k was given to us in minutes. So if you take out your calculator and take 0.693 over 2.97 10 to the negative second, we get 23.3 minutes. So that's part B. Part C of the question, how much time is required for the concentration of A to decrease to a specific amount? Here we're going to use the integrated rate law, which, as we've noted before, takes the format the natural log of A equals negative KT plus the natural log of the initial concentration of A. Well, here they're saying this is the concentration at some time, and we want you to find the time. Okay, so this is the concentration. We'll plug that in for concentration of A at the time. Equals negative K. We know from above that K is 2.97 10 to the negative second. Times time, a variable that we're solving for. Plus, let's see, initial concentration. They gave that to us in the original question stem. So we get to plug in natural log of the initial concentration of A, 2 times 10 to the negative second. And at this point, you can pull out your calculator. There's a bunch of things to take logarithms of. The natural log of 2 times 10 to the negative third is negative 6.215. We'll round at the end. And the natural log of 2 times 10 to the negative second is negative 3.912. Simplify that a little bit. And get t alone. And if you crunch the numbers, we get 77.5. The units here are minutes, because they've been working throughout the problem. They gave us units of time in minutes.